Okay, so I'm going to give a session preview of the types theory session. It's a little bit confusing because there's types 1, types 2, type 3, and the type theory. I guess this is a more theoretical, even more theoretical session. So what the type theorists are doing, well, we're simply dealing with type theory. And in my opinion, type theory is a language of abstractions. So we're trying to deal with abstractions. So basically, we're doing two things. One is to find abstractions for interesting concepts out there. And then we're going to implement it because we are the one who created, so we might very well be the one who know what exactly to try to implement. So you are going to see papers trying to dealing with this tool. And in this session, in the type theory session this year, every paper takes dependent types for granted. I don't have time to explain these, but they are already very powerful. And we're not satisfied. They're trying to find even more things and then add that along with the dependent types all together into the theory. So that's what this session is about. So since this is about finding interesting concepts, I'm going to briefly introduce the interesting concepts that each paper is trying to introduce. Okay, and then that will be my preview. So the first interesting concept is about parametricity. So parametricity, many of you probably know it, so please bear with me. So one interesting thing that you can prove using parametricity is that any function of type for all A to A, so A here stands for a type, any function of this type must be the polymorphic identity function. Okay, that's the only solution. The idea is that because you cannot really see what A is, so the only thing you can do is to get the input of type A, which is something unknown, and then return it. And you can prove that that's the only case. But this theorem is a meta-theoretic theorem. You cannot prove it inside of theory usually. You can prove it outside of theory as a meta-theoretic analysis. And the trick here is to interpret types as relations. So you plug in a interesting or spatial relation for the type A, and then you can improve this theorem. But this is outside of the theory. Okay, so this is, I should say, usually outside of theory because we are going to have something called internal parametricity. So that is the concept that the two of the papers in this session are going to deal with. The idea is that this is usually meta-theoretic, but maybe there's a way to make it available, accessible inside of theory, so you can actually prove things like this inside of theory. Okay. So as I said, there are two papers. The beginning two papers in these two sessions are going to deal with internal parametricity. And you can see that there's a keyword on the first paper, which is without the interval. So that's what I'm going to introduce a little bit further. So why is there's an interval that is relevant here about parametricity? This goes back to the cubical type theory and homotopy type theory, but I'm going to just focus on one single concept here, that is path, that path in the topological space. So if you learn a little bit about if you know a little bit about the classical topological space, this idea of path that is kind of defined as a continuous function from the standard interval 0 to 1 to the topological space. So imagine that you are moving from 0 to 1, and that is kind of plotting the path in the topological space. So that's how cubical type theory defines a path. It's defined as a function, a continuous function from the interval that is kind of just added to the theory to the any space. So that is path. And then some researchers figure out that, well, parametricity is about types as relations. And relation also kind of like something between the two things. And by introducing a new kind of intervals, and which is called bridge interval in the literature, then you can also kind of mimic this idea. So you can define a relation as a function from this spatial bridge interval to whatever like space you are talking about. And this is the basis of these two papers. The first paper says that yeah, okay, we know this, but we also found a way to have internal periodicity without the interval. That's why it's so important in the title that they say that we can do it without this. And the second paper didn't try to remove the interval, but it's still a significant work because then they implement this inside of the cubical AGDA, which requires lots of work. They also have to modify something of the fate of AGDA, but I don't have time to go into detail. Please don't. They're all very exciting, and then please just go to the session and listen to the authors, or maybe read the papers. Okay, so this is what the first two papers are dealing with. The next cool concept is indistinguishability. The idea is that the low-level observer should not be able to distinguish the data as high level. For example, like a stranger on the street should not know what your passwords are, and the way to formalize is that it couldn't distinguish whether your password is empty or very long. Okay, it couldn't distinguish anything. So that's an indistinguishability. And this paper, the third paper, is to say that how to internalize this concept inside of type theory. So it's again trying to find interesting abstractions, new abstractions, to account for the interesting concepts out there. And the idea here is to make the information at the higher level judgmentally equal to the lower level. So judgmental equality is a kind of something in the dependent type theory. The basic thing is that if something is judgmental equal to the other thing, you really cannot distinguish them inside of theory. So this is forcing the data at the higher level to be judgmental equal to a lower level. Okay, so now you see that, wow, whether something is judgmental equal to other actually depends on who is seeing it. So that is a complication of this theory, but they managed to sort out the details. And again, I will invite you to go to the talk. The final thing is the implicit complexity, but I want to explain a little bit what we mean by implicit here. So complexity classes like polynomial time or NP, it could be, there are two ways to handle it in type theory. One is explicit. It means that you are tracking the amount of resources you are using at the index of types. So maybe your types now is augmented with the number of steps you are taking. So that can be used to track running time, for example. But there's another style to do this, which is to come up with a type system that doesn't explicitly say the amount of resources. But then you can prove as a meta theory, saying that anything that can be typed does have the property that the thing you are defining is in some complexity class. So that is kind of implicit. You are not writing down the number, but you can prove that anything that can be defined must belong to a certain complexity class. And it has been known that you can actually use linear types for polynomial time. And this is something cool. And this paper is to combine this. Again, we want dependent types. Previous work on the linear types is only for the simple types. So this paper is trying to bring this idea of using linear type for polynomial time into the world of dependent types. So that's basically the main point. You can see that the title really just combines these two. So that will be the last paper of this thing. So so all these amazing talks will start in 1 hour and 45 minutes, just upload. So I welcome all of you to attend the session. Thank you. Okay.